Okay friends, welcome back. Again we are going to discuss about linearized PLL model. So linearized PLL model input signal is given to phase detector and through phase detector it is given to VCO. And from VCO oscillator to it, the output will be retained, and from the VCO the phase detector will be connected. So the basic PLL architecture is shown in figure consists of a phase detector and a voltage controlled oscillator. The phase detector compares the phase of an incoming reference signal with that of the VCO and produces an output that is some function of the phase difference. The VCO simply generates a signal whose frequency is some function of the control voltage. The general idea is that the output of the phase detector drives the VCO frequency in a direction that reduces the phase difference. That is it's a negative feedback system. Once the loop achieves lock, the phase of the input reference and VCO output signal ideally have a fixed phase relationship, most commonly 0 degree or 90 degrees depending on the nature of the phase detector. Next, we are generally interested in the phase relationship between the input and the output signal. Here the block diagram is here clearly representing. Next, in this model, the input and output variables are phases rather than the time waveforms of the actual inputs and outputs. Another consequence of choosing phase as the input to output variable is that the VCO, whose output frequency depends on a control voltage, is modeled as an integrator since phase is the integral of frequency. The VCO, again constant KO, has units of radians per second per volt. The phase detector is modeled as a simple subtractor that generates a phase error output. The phase detector is modeled as a simple subtractor that generates a phase error output, that is the difference between the input and the output phases. To accommodate gain, scaling factors and the option of additional filtering in the loop, a block with transfer function is included in the model as well as it is given in the block diagram. First order PLL. The simplest PLL is one in which the function h of s is simply a scalar gain because the loop transmission then possesses just a single pole. Thus type of loop is given as first order loop. And again, aside from simplicity, its main attribute is the ease with which large phase margins are obtained. Bandwidth and steady state phase errors are strongly coupled in this type of loop. Generally, we want the steady state phase error to be zero, independent of bandwidth. First order loops are infrequently used. We may use our linear PLL model to evaluate quantitatively the limitations of a first order loop. The input output phase transfer function is readily derived. Phi out of S by phi in of S is equal to K naught KD by S plus K naught KD. So the closed loop bandwidth is therefore omega h is equal to K naught into KD. To verify that the bandwidth and phase error are linked, let's now derive the input to error transfer function. Phi e of s by phi in of s is equal to s by s plus k naught into kd. If we assume that the input signal is a constant frequency sinusoid of frequency omega I, then the phase ramps linearly with time at a rate of omega I radians per second. Thus, the Laplace domain representation of the input signal phi in of s is equal to omega I by s square. Phi e of s is equal to omega I by s of s plus k naught into kd. The steady state error which a constant frequency input is therefore limit s tends to 0 s of phi e of s is equal to omega I into k naught into kd is equal to omega I into omega I by omega h. Next, for first order PLL, the steady state phase error is thus sim- simply the ratio of the input frequency of the loop bandwidth. A 1 radian phase error results when the loop bandwidth loop bandwidth. In general, a non-zero voltage is required to drive the VCO to the current frequency. Since the control voltage derives from the output of the phase detector, there must be a non-zero phase error. To produce zero phase error, we require an element that can generate an arbitrary VCO control voltage from a zero phase detector output, implying the need for an infinite gain. To decouple the steady state error from the bandwidth, however, this element needs to have infinite gain only at DC rather than at all frequencies. An integrator has the prescribed characteristics and its use leads to a second order loop. The 90 degrees negative phase shift controlled by the added integrator has to be offset by the positive phase shift of a loop stabilizing zero. Second order PLL. The zero should be placed well below the crossover frequency to obtain acceptable phase margin. In this model, the constant Kd has the units of volts per second because of the extra integration. As the loop transmission magnitude increases, the loop becomes progressively better damped because an increase in crossover frequency allows more of the zeros positive phase shift to offset the negative phase shift of the poles. It is very straightforward to show that the phase transfer function phi out by phi in is equal to tau z s plus 1 by s square by kd k naught plus tau z s plus 1. From which we determine that omega n is equal to square root of kd into k naught and psi is equal to omega n into tau z by 2 is equal to tau z square root of kd k naught by 2. Furthermore, the crossover frequency for the loop may be expressed as omega c is equal to omega n power 4 by 2 omega squared z plus omega n square root of 1 by 4 into omega n by omega z power 4 plus 1 whole power 1 by 2, which simplifies considerably if the crossover frequency is well above the zero frequency as it often is. Omega c is approximately equal to omega n square by omega z. Next, the loop transmission of first order PLL should be like this. The loop bandwidth may be adjusted independently of the steady state phase error, which is zero here. The stability of this loop can be explored with the root locus diagram. Here root locus diagram also obtained. Next, second order PLL. The above figure shows that the crossover frequency always exceeds omega n. Omega n is equal to square root of kd into k0 is the extrapolated crossover frequency of the loop with no zero. Finally, it should be clear that increasing the zeros time constant improves the damping given a fixed omega n. Thus, the bandwidth and stability of a second order loop may be adjusted as desired while preserving its zero steady state phase error. Phase detectors.